autoencoder, which is today the topics, and we done with artificial neural net, and there's some. The next topic is autoencoder. I'm going to explain what it is. And the first here is, the title is unsupervised. So I think you guys are familiar with what the supervised learnings and the unsupervised learnings at this moment. But let me repeat what, so supervised learning is we need input and output or labels at the same time to train the models. So for supervised learning is trying to figure out the relationship between the input and outputs. Okay, so we need X and Y at the same time. But on the other hand, unsupervised, basically for unsupervised, we do have input only. We don't have any associate outputs and labels. Many times we don't, but so that's the only information that available to us is input data set. So unsupervised learning refers to most attempt to extract information from the distribution. We do not require human labor on the annotating. That means we don't have any labels and the outputs. So for unsupervised learning, the main task is going to be to find the best representation of the data. So if you learned machine learning, there's two major topics belong to unsupervised learning. Is the first one will be the clustering. Second topic is the dimension reductions. So clustering is, I think, one of the famous method in the cluster is k-means. So how do you cluster when you have only X informations, input informations? And the second, the famous one is dimension reductions. We want to reduce number of features in the input space. So I think the most famous one is a principal component analysis, PCA. And okay, so for here for autoencoders, we're only talking about the dimension reductions. We're trying to attempt to compress as much information as possible in a smaller representations. That means, suppose you have, say we have 100 the features, and if some of xi's are correlated or dependent, that means or correlated or dependent, that means if we know, say I or j's are either dependent on correlated, that means if we know I, we can refer the, so we don't, these two we can think of as a redundant information. So we don't need to carry all of the features. Right? So in that case, we can get rid of maybe like one of them. So we can reduce the number of features. That means we can represent same amount of informations in a smaller representations or in a smaller number of features. We want to preserve as much information as possible, but at the same time, we want to keep the representation as simple as possible. I mean, one of the reasons that is the dimension reduction is if that's also related to regularizations, overfitting problems. So if you're trying to get the smaller number of representations, we can avoid overfitting problems as well. So another, I mean, these are the different phrase just talking or describe what dimension reduction is. And the modeling consists of finding meaningful degree of freedoms that describe the data or signals, right? And they are lesser dimensions. That's what dimension reduction are about. For autoencoders, it's like a deep learning version of unsupervised learning, or I will say nonlinear version of PCA, or say principal component analysis, or nonlinear version of dimension reductions. Nonlinear. So the definition of autoencoder is it's a neural net trained to attempt copy its input to the outputs. So it's we want to generate output from the inputs. And it consists of two parts. One is encoder, and the second part is decoder. And I guess at this moment you guys know what I'm talking about, but don't worry. So we have inputs. And remember, this is unsupervised, so we don't have Y. And for F, so we generate Z space, but it's smaller dimension, it's smaller number of smaller features. And I want to get another mappings or functions or whatever, and I want to reconstruct. So starting from X, and it end up then copy or duplicate another X, but in the middle we have Z. But I will say the size is much smaller, much smaller than X. Right? So that means F will be X. And probably this one's better to explain it. Say, suppose we have input X. This is another input X. Say our purpose is to recover the input data using neural net work. And what kind of structure do you guys can think of to recover the input data? Say this is like X1 and X. And you can think of as these neurons. I guess probably this one is the simplest neural net, and we can recover the inputs too. And what's the weight associated? What's the weight's gonna be?
1.
Right? Then we can recover the inputs. It's done. But as you can see, this is trivial solutions and structures, and there's no dimension reduction part. So let's instead of having this kind of the simple structures, and why don't we have this kind of structure? Again, here we have X as input, and we're gonna have X as output. I mean, we don't have any outputs, but I treat X as output and X as input, and here is output. the key difference between these two, we have here, we kind of squeezed in the middle. So we have we call this kind of bottleneck structure. So we have inputs and hidden layers and another input or outputs. And suppose we have, say, like 100 and 50 and 10, 2, 10, 50, 100. And we call it, this part is encoding, and the later part is decoding. Okay. And the thing is, for the data set, we have, suppose we have only 2 neurons in a latent space. That means, if you're just thinking about decoding part, somehow we have to recover the value of 10 neurons from 2 latent variables, right? And on the other hand, for encoding part, from 100 neurons, somehow we have to encode, we have to compress the informations into 2 neurons. So we believe that if somehow, if we are able to successfully generate or recover or duplicate from X, that means here in latent space is going to carry key important informations. Suppose with these, we have only 2 neurons, and over here some of them are redundant, right? Then here is, we don't have enough space or memory to carry the redundant information as well. So in order to have this kind of autoencoder structures, and as well as to recover the input data set, during the training process, somehow here the information is going to concentrate. To learn the encoding of the inputs so as to recover the original input from the encodings, as well as possible as. Okay. So that's the key structure of autoencoder. We starting from recover the input data set in an unsupervised unsupervised manners, but we learned that this one is acting as dimension reductions. And let's think here, we try to say this is original space and the latent space. And here, in the simpler case, say, in the original data set, it's a kind of distributed in 3D space, the original space, or the higher. And here it's a smaller space. And F is nonlinear mapping. F is and it's encoding. G is nonlinear mapping. It's decodings. What I'm trying to do is that starting from X, okay, then from the F nonlinear mappings, we will get Z, and from G nonlinear mappings, we will get X prime, and from the training data set, what we want to do, I'm gonna find f and g to satisfy these. So I want to get, right, so as close as possible. That's what I'm trying to do. So as you can see here, this one is x prime. And remember, there's no y in this case because it's unsupervised learning. We're starting from x, we get encodings, and from in the latent space we do decodings and see if these two are close enough or not, or trying to minimize trying to as close as possible to pick right f and g's in autoencoders. And let's try to implement it, the autoencoder structures with MNIST dataset. And this is going to be the exact structures that I'm going to implement. And since, let me see, this will be the structures. The input is, as you can see, it's a 784 because that's the flattened, and the output should be the same. And I decide to have two neurons in the latent space. That means start from 7084, I'm going to squeeze down to 2, and I'm gonna reconstruct it. Right? So this means say we have MNIST data set like that. We have all the values in each pixel, right? In total, it's going to be 784. But somehow, suppose we say it's a good, we trained where that means there's only 2 pixel informations are necessary. That's what this autoencoder means. All right? And instead of for MNIST data set from 0 to 9, so this is like 10 digits. But in this case, for demonstration purpose, for the simplicity, I'm gonna use only 1, 5, and 6. I mean 3 digits to visualize in 2-dimensional space. So I'm going to only use 3 of them. Right? There's no specific reasons because I want to visualize to see in what kind of the things happening in the latent space. Right? So I decided to have 3 digits. And let me see. Okay, let's switch to here. Do you guys have any questions so far? Because I'm gonna move to here and trying to run the autoencoder with you guys to see. Any questions, conceptual questions on related to autoencoder so far?
No, that's okay.
Okay, let's see. Let's move on to. So these are the same. I mean, here if you go and teachings and artificial intelligence, and for deep learnings, let me see autoencoder. I mean, these are the same materials that you guys can see. Again, we need NumPys and Matplotlibs and TensorFlow, things like that. And we need MNIST data set. And here, you don't need to worry about it. The thing that I did is because I decided to use only 3 of them. So in here, in the training data set, labels and if they say 1 and 5 and 6, that's I put it in the training index and the test index as well. I repeat it. So so these are the number of training data set, and this is the number of testing data set. And here, only thing is that we have this 1 and this 5 and this 6. That's all we have. And let's move on to how to construct or design, define the structures. And remember it, like 784 and 500, 302. And I like these. So it will be like here, the number of inputs, like that. And then the number of encoder, the first layer, first hidden layers and the second hidden layers. And this is number of latent. Just remember is I'm squeezing down from 784 to 2. That's kind of amazing. And this is the decoding part. And remember is numbering is 1, 2, and latent, and 2, 1. That's how I define it. And here we have again weight and bias. I'm using the dictionary type. Encoder 1, encoder 2, latent, decoder 2, decoder 1, and reconstruct. There will be this gonna be the same as the outputs. So here I initialized it with the Gaussian normal distributions with the proper shape or size of the here. And placeholders, this is important. As you can see, remember like in here in like for supervised learnings, this is what you see always. But since we're talking about unsupervised learnings, we don't have any Y for the placeholders. Okay, so we don't have. Just only thing it's known to us is input. And let's see how to build the models. And this is same as the ANN structures, but I split it into decoder and encoders and the decoders. And for encoders, I will get X and the matrix multiplication to weights, and we add the bias. And in here for nonlinear activation functions, I just happen to use the tangent hyperbolic. There's no specific reasons for that. And we have seen another hidden layers, I repeat it. And for the latent space, so up to here. So this, in this encoder functions, the latent, the value, it will be the output. And for the decoding part, we will receive the latent, right? And we'll do the decoders and nonlinear activity functions, another decoders here, and this will be the outputs, but it's gonna be the reconstruct of X. So I would say reconstruct. So this will be the outputs. And so next thing is how we have to define the loss functions, and we have to assign what kind of optimization solvers that we're going to use. And as you can see here, it's similar to regression problems. And so this will be the target. And I mean, let me see. It will be one is the predicted one, the other one. Let me see. I will say this is X. Right? So there will be X, and this is I will say so X hat, which is the predictive values from the encoder and decoders, and X is the true inputs. I want to minimize the errors, right? So that's what I'm trying to set this as a optimization objective functions. And here for optimizers, so why don't we use atom optimizers? And this is alpha, is learning rate. And for latent values, starting from X and weight and bias, we'll get the latent. And from the latent, we will get reconstruct. And for the loss functions, we'll X and reconstruct and subtract and square them. And again, it will be the batch gradient descent. So we have to do reduced means to get the scalar values. and I want to minimize that with this running rate using the atom optimizers. That's how we define it. And here is batch size and maximum number of iterations and things like that. And here we do have, in this case, we have to define our batch makers for the training and the test. So I put the batch size, and we get randomly selected among the number of trains, and we get it. And so here's start open these sessions and initialize them. And for the batch makers, I will get train X. We don't need Y, and this is the only information that we're going to try. We're going to use it, and for this, for optimization from, we feed X. We don't have Y's here, and run it. Okay. Once we're done, and let's see. Let's run it. I don't know why. Let me see. Run it. So okay, so it's a iteration process, and you can see as it progresses, the loss or cost gets smaller and smaller. We're done. We complete, and let's see. Here I got only one of them in the test, and feed that to that. Now here is not from it's not from the training. It's from test, and feed the reconstruct values, and I plot it. And this one was the input, okay. And as you can see on the right side, this one is the reconstructed image. What do you think? Do you think it's a reconstructed web, or it's not? Let's try another one. Okay. Okay, I mean, let me see here. I mean, this is the inputs and the autoencoder structures, and this is the reconstructed image. And hoping that these two are similar enough. Of course, I think we can do better having like different, add more layers and put more neurons, but I think it's good enough. What I'm trying to do is that among the testing data set, I just get 500, okay, and then created the latent space, and I want to plot all the data points here. I mean, this is 500 data points from the training data, I mean, from the testing data set. But it turns that in our designed autoencoder structure, we have only 2 neurons in the latent space. So say this is Z1 and Z2. Z1 and Z2, I plot them. And also I mentioned that instead of using 10 digits, I just pick 3 of them. It's 1, 5, 6, and I plot it in latent space. What you guys can see is that here is 1 and 5 and 6, and as you can see, there's some kind of clusters. So in the latent space, these are related to 1, and these are related to 5, and these are related to 6 in the latent space. Do you guys see what I'm trying to do? I mean, this is the key, the step or moments in autoencoder. So that means if say we put the classifiers probably like that, and here there's some kind of the vague reasons, but of course obviously these are the 6 and these are the 5 and these are the 1. I think we can create decent nonlinear classifiers if we applied it into latent space instead of applied it in the original space, which is 784 dimensions. Compared to that, here is just 2-dimensional space. But the good thing is, because you use autoencoders, we believe that the picture that the latent space that you guys is looking at is kind of the most independent or uncorrelated space. Okay. So next step, what I'm trying to do is that, okay, here it's latent space. What if I just pick here? I mean, anyway, pick here, say in 5 and 4, 5,4, and put it in the latent space and compute it for decodings, and we can reconstruct it. And what kind of the image that you guys can supposed to see? You guys, let's see. So I'm going to pick here 5 and 4. And 4. Now what I put it here in the latent values and reconstructed it and run it and I want to plot it. You guys are with me, and you guys know what I'm trying to do. So here is kind of the cluster of green and cluster of 6, and let's see. I pick 5,4. That means here, this guy, and let's run it. And you guys ready to see? All right? And this one is generated. It's a fake. But we generated the values among here it looks like it's 6. And let's see, let's pick here 6, minus 2. Looks like 5, right? But this is a generated fake data set. I mean, fake image. We never seen in the training data set. It doesn't exist. It's a fake. So basically what I'm saying is that using this kind of autoencoder structures and put the random values and in the latent space, I can generate the fake image as much as I can, as much as possible. What about here? 2,1. Let's see this. So if I pick here, what kind of image they use? You guys expect to see here? What do you think?
6 maybe.
So is it in the latent space, these are the 6 and these are the 5, right? But it's overlapped. So like I said, let's see, it's mixed. Someone might see 5, someone might. I mean, you guys can see 5 and 6 at the same time, which makes sense because it's a latent space. We know that here. Does that make sense? Or no?
Yes, it makes sense.
Yeah, yes.
Okay, so let's move on. Let me see. Okay. I think just what here is like, I can generate a bunch of fake 1s and a bunch of fake 5 and 6, things like that. And now we're starting from the autoencoder is trying to duplicate the input, right? But once we have this kind of bottleneck structures, we can use autoencoder as a feature extractors, because we believe that this in latent space and the dimension reduction as well. But from now on, I mean, if you just thinking about this part is latent. So we have small number of neurons, and you can treat it autoencoder or decoder part of autoencoder as a generative models. As a generative models, we can generate something from latent space. What do you mean by the generative capabilities? And you know that this is the nonlinear mappings from latent space to the original space. And we can say the here, and we say the here is, I don't know, is some kind of the Gaussian distributions, whatever. And just pick random numbers and doing like this decoder. We will get some values in the original space. That's a generated one. And let me see. So that's how I do. And probably just like here, I will generate the 5, things like this. To get, let me see. Yeah. Let's think about this one. This is the most favorite one that I like to here. And let's think about, we have this kind of pictures. We have x1 and x2. We have the pictures or 2 inputs, and someone play golf. I'm trying to interpolate in higher dimensions or original dimensions. Here, say this is 28 by 28, the image, whatever. I mean, then it'll be in each pixels have individual values, right? And if you say this is x of 1 and x of 2, and trying to get maybe x in the middle, I'm trying to interpolate it in the original space between what will be the image between the x of 1 and x of 2. What kind of image?
A mix.
Right. In the probably the best thing that you can do is for each pixels, right? Say this one is say P1 and this is P, and probably the image over here will be, I mean, right, that's the best thing that I can do. So each pixels, I will just take the mean of that, and if you do, this will be the interpolation image in the original space. But as you can see here, okay. And what do you mean by this is say it's in the conceptual way, what you did is you just here is this is x1 and this is x of 2. In the original space, probably that's how you do. And you just take the pick any values in between. But it turns out that probably in, if we call it, this is manifold. And we know that it says it's starting from, if you just get the physical meaning or physical sense of this, is what this guy is doing in the picture is it's trying to play golf, right? And swinging from here to here. So what should expect is like starting from, and this one, right? You guys know what I'm trying to say. And this one is more makes sense to us because we know what the guy in the picture is, it's doing it. So just having the middle values for each pixel doesn't make sense. We have to pick the values in latent space. We have to do interpolations in manifold. We have to do interpolations in the latent space instead of we doing interpolations in the original space or doing interpolations in the higher dimensions. That's what this everything is all about. So you guys, so for the interpolations, if we do original space, probably I will just and you guys can hear me?
Yes.
What about Thomas?
Yeah, sorry. Again, I tried to figure it out why my computer cut my sound.
Okay. So now,
Yeah.
can I move on or? Okay.
Yeah. Continue. Sorry.
So if you do interpolations in the higher dimensions, probably x and x prime, probably this is what we're trying to do. But this is not the right way to do. We have to do in that kind of in linear interpolations in latent space because that's more makes sense. Then we have to right is unmapped to the original space. That's what we are supposed to do it. And that's, I think, is nice illustrations for that. And I think it's another one of the last topics. Okay, here is there's the walk in the latent space. So you have to walk in the latent space instead of you used to walk in the original space. What I mean by, say we just walk it from here. And here we know that starting from 5, you got 6. And I'm hoping that if you walk in the manifold or if you walk in the latent space, there is smooth transition from, you can see the transition from 5 to 6. See that you guys can see the transitions from 5 to 6 in the MNIST data set. So it's more meaningful, or it makes sense you walk or you're talking about in the latent space instead of the original space, because original space in the higher dimensions, a lot of informations are redundant, right? So for generative models, it generates something that makes sense. But as you can see, so some of the results are unsatisfying, but that's okay, because we can the network that I've used it is for demonstration is too simple, but it's okay. And the building, let me see, and this is the motivations to the variation autoencoders and the GAN, which is the key things, the famous one, and the things that I'm going to talk about after midterms. Right? So this will be the motivations, but the conceptual wise, the autoencoder is good enough to understand dimensional reductions and the generative models. What else? And things like that. Okay. Let me see. That's all the materials that I have for related to autoencoders.